Okay guys, this is our first video lecture. We're going to pick up where we left off in class. In class we had started this packet of notes, the Chapter 10 notes on structure and bonding. We had covered ionic bonding, and we had moved on to the real topic of the chapter, which is covalent bonding and Lewis structures. So, typical Lewis structure is shown here, and we had explained that each little line here represents two shared electrons, so that is the covalent bond. That is two electrons that are shared between the carbon atom and the hydrogen atom. You can have double bonds like this, that would represent four electrons shared between the carbon and the oxygen. You have lone pairs, also called unshared pairs, or sometimes non-bonding pairs. You see those four dots up there on the oxygen, that's a couple of lone pairs. They're not involved in bonding. Those electrons just happen to belong entirely to the oxygen atom. The big overriding thing in Lewis structures is the octet rule. So each atom wants to look around and feel like it's in contact with 8 electrons. So if you look at this carbon atom here, that carbon atom feels like it's in contact with 1, 2, 3, 4, 5, 6, 7, 8 electrons. If you look at the oxygen atom feels like it's being touched by 1, 2, 3, 4, 5, 6, 7, 8. So the oxygen atom's being touched by 8 electrons. So they're both happy. They both satisfy the octet rule. One element that never satisfies the octet rule is hydrogen. Hydrogen only ever gets 2 electrons rather than 8. Also, another thing to note here, you may have noticed that these electrons in the middle here in the double bond, they got counted twice. So these 4 electrons are counted by the carbon atom. These 4 electrons are also counted by the oxygen atom. They're sharing those electrons, so both of them get to count them. If you counted how many electrons are in the entire structure, you should come up with 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 electrons total, but each element feels like they have 8, except of course hydrogen, who feels like it has 2. So that's a Lewis structure. And you have to get to the point where we can give you something like CH2O, and given this, you have to be able to derive this. So the rules for doing that are on the next page here, and it looks a little bit lengthy, but they're really not too hard to master, and we're going to do quite a bit of practice with them here. The first thing you always have to do when you have to draw a Lewis structure is you have to calculate the number of valence electrons that are going to show up in that structure. Calculating the number of valence electrons is super easy. You simply determine how many valence electrons each element brings into the structure. Valence electrons, as I've mentioned previously, those are electrons that are involved in forming bonds. The valence electrons are the electrons that are shown in a Lewis structure. So, how many valence electrons does an element bring to the party? Real simple. You look at your periodic table here. You see your group numbers, like carbon here is in group 4A. Each carbon atom brings 4 electrons to the table. Oxygen here is in group 6A. Each oxygen atom brings 6 electrons in. Chlorine here. Chlorine is in group 7A, so a chlorine atom brings 7 electrons. You may have noticed 2 different numbering systems on our table. There's actually 3 different numbering systems for the groups. This system here is the American system, where we call this group 3A, 4A, 5A. The European system calls this group 3B, 4B, 5B. The international system, the official system, just numbers them groups 13, 14, 15, 16, 17, 18. If you have one of these tables where the group numbers are 2 digits and you're wondering how many electrons does an element bring in, well, take a look here. Fluorine's in group 7A in the American system, so you'd say it brings 7 electrons. If you have one of these international tables, just cover up the first digit. Fluorine is worth 7 electrons. Oxygen is worth 6 electrons. So that's how you figure out how many valence electrons are associated with each atom in a structure. Hydrogen's worth memorizing because he's pretty common. Hydrogen is only worth 1 electron. So if we asked you to come up with the Lewis structure for that CH2O and you had to count up electrons, you'd say, oh, I got 1 carbon atom. Say we're doing CH2O. 1 carbon atom, that's 1 times 4, 4 electrons. You have 2 hydrogen atoms, so it's 2 times 1, 2 electrons. 1 oxygen atom, 1 times 6 would be 6 electrons. Add it all up, you should have 12 electrons. So what that means is, in the Lewis structure for CH2O, you have to show where 12 electrons live. And we just saw that on the previous page here. There's our 12 electrons total in the structure. We have a double bond, a couple of single bonds. We also have a couple of lone pairs, and that's 12 electrons. So that's how you count up electrons. Now, for ions, as you recall, are any chemical species with a charge. And it seems a little weird at first, but if you have a negative charge, do you subtract electrons? No. If you have a negative charge, you add an electron for each negative charge. So if you were doing the Lewis structure for something like, say, cyanide here, Cn minus 1. Hey, 1 carbon atom is worth 4 electrons. 1 nitrogen atom is worth 5 electrons. That negative 1 charge is worth 1 additional electron, and the total number of electrons present in the cyanide ion would be 10. So if you have a negative charge, you add in 1 more electron. Any polyatomic ion that happens to have a positive charge, you subtract 1 electron for each positive charge. I know it seems backwards, subtracting for a positive, but that's the way you count up electrons. Now, the second step when you're drawing a Lewis structure is you draw a so-called skeleton structure. Skeleton structures are pretty easy to do. Some people get a little bit hung up on them because they don't know some simple rules. One of the rules that you should definitely know when you're drawing that skeleton structure, never put hydrogen in the middle of the structure like I've shown over here. You can never, ever, ever have your hydrogen bonded to 2 different atoms. So hydrogen can never be your central atom. Never, never, never. You get pretty used to this over time. You notice that hydrogen is always on the outer periphery of a structure. You see how here the hydrogen atoms are all along the outer periphery. There's another element that's just like that, where it's always on the outer periphery, and that is fluorine. So fluorine atoms, hydrogen atoms always live on the outer edges of a structure, never in the middle. So for a skeleton structure, you simply put 1 element in the middle and surround it by the other elements connected by single bonds. So if we were to do the skeleton structure for our CH2O, well, we'd start with the carbon in the middle. A good rule of thumb, whatever element is listed first in the structure, that's the element that usually goes in the middle. Some people use a different rule. They say the least electronegative element usually goes in the middle. That will work too, but typically it's the first element listed. So you have your carbon, you connect it by single bonds to the other elements. Oops, that's not an oxygen, that should be a hydrogen. And that would be the skeleton structure. Skeleton structure simply means connect everything with single bonds. So that's your skeleton structure. And remember, hydrogen only ever gets 2 bonds, so hydrogen has to be on the outer periphery of a structure. The third step in drawing Lewis structures says to complete the octets of the outer atoms by drawing electron pairs on them. This is so easy. You take a look at your skeleton structure. I'm going to get rid of that glare here. I hope that do it. Okay, so here's our skeleton structure. When it says outer atoms, well, that's an inner atom. Those are outers. You don't complete octets on hydrogen. Hydrogen never, ever gets an octet, right? So you complete the octet on the oxygen here. Right now, that oxygen has 2 electrons. It needs 8. Well, now he has 8. So when it says to complete the octets on the outer atoms, that's what it means. Next step, you want to stop and count. So the fourth step here says stop and count. How many electrons do we have in our structure? Well, if I stopped here and just counted, I would end up counting, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you might recall that for this formula, I should have 12 electrons. So at this point, whatever I do, I better not add any more electrons. I better not lose any. I've got the correct number right now. All I can do now is rearrange electrons some. I can move them around. So the fifth step here, says, once you have the correct number of electrons in your structure, check to see if everybody has an octet. In other words, is everybody a happy camper? Does everybody have 8? And you can see from our structure here, no. Who's missing their octet? Carbon. Carbon right now feels like it only has 1, 2, 3, 4, 5, 6, but it really wants to have 8. So the rules say, hey, if your central atom doesn't quite have an octet, what you're supposed to do is take a lone pair and turn it into a bond. You can do that. It's quite legal to do that. So if you're looking to do that, you look up here at your oxygen, you see these 2 electrons here. We're going to take those away as a lone pair. They're not going to disappear. We're just going to erase them as a lone pair. And instead of being a lone pair, they're going to show up as a bond. And that's your Lewis structure for the formaldehyde. So that's a real important concept there, is that you can take lone pairs, move them around, you can take pairs of electrons and move them places. We just took a pair of electrons here and plopped them in the middle as a bond. And there's our Lewis structure of the formaldehyde. So what you want to do now is practice a little bit. If you flip the page here in your notes, hopefully you've printed out these notes and you have them available. I gave them to you in class last time I saw you, so hopefully you still have them. You want to practice, see if you can come up with the Lewis structure for these compounds here. We have carbon monoxide, We have the cyanide ion. There's some more on the next page. You might want to pause the video at this point. Just pause it. See how far you get on your own doing these ones. And after you've tried them, turn the video back on. I'm going to go ahead and work through these ones, and you can see how they're actually done. So, for our carbon monoxide here, our carbon monoxide CO, first step, count how many valence electrons are available. We have one carbon atom, so that's going to be 1 times 4. That's worth 4 electrons. One oxygen atom, so that's going to be 1 times 6. 6 electrons. When we're done with this structure, it had better contain 10 electrons. Now, where did the 4 and the 6 come from? Carbon lives in group 4. Oxygen lives in group 6. So, we got to come up with 10 electrons. That's our first step, counting electrons. The second step, you draw your skeleton structure, single bonds. No real central atom when you only have 2 atoms, so we'll just do carbon connected to oxygen. That's our skeleton structure, single bonds. Third step says complete the octets of the outer atoms. Well, let's go ahead and do that. And what you'll see here is we have way too many electrons. This structure right now contains 6 electrons there, 6 of them there, so that's 12 total, 13, 14. So we have 14 electrons, we're only supposed to have 10. And I think at this point I'm going to switch over to the whiteboard. So let's see if I can draw this in effectively with the whiteboard. So my carbon monoxide right now I have drawn like this. And I have 4 too many electrons. I have an extra 4 electrons. Hey, no problem. I'll just lose 2 of them from here, 2 of them from here, there. Now I have 10 electrons like I'm supposed to. So now I've got the correct number of electrons. I have to ask myself, is everybody happy? Do they all have their octet? Heck no, they each only have 6. How do I solve that? Hey, I can take a lone pair, transfer those electrons from the lone pair into a bonding pair. At this point, my carbon's happy. My carbon has his octet. My oxygen still only has 6. What can I do? I can take a lone pair, turn it into a bond. There's my carbon monoxide. It's the carbon with the triple bond to oxygen. It's got a lone pair on the oxygen, and it has a lone pair on the carbon. That's carbon monoxide. That's the Lewis structure for CO, a deadly poison, of course. It kills people each year when their furnaces aren't working correctly and it starts to put carbon monoxide out. It can kill you. You go to sleep and then you wake up dead from breathing that in. So there's that Lewis structure. Let's go on to the next one. Again, you might want to pause this and see if you can work through the next one, which is the cyanide ion here, all on your own. Now, I'm going to show you how to do the cyanide ion. Cyanide, you got 1 carbon atom, so that's going to be 1 times 4 is going to be worth 4 electrons. You have your 1 nitrogen atom. Nitrogen's in group 5. Your nitrogen here is in group 5. So nitrogen brings 5 electrons in. You also have that -1 charge I got a -1 charge. A -1 charge means it has 1 extra electron. Add all this up, and you'll see that cyanide ion will have 10 valence electrons in it. Now, you start with your skeleton structure again. So you'll have your carbon atom, single bond to nitrogen. You might already see where this is going to end up. You notice over time you have certain patterns. If you have 2 atoms and 10 electrons, it always ends up with the same sort of thing. So anyway, there's our cyanide as a skeleton structure. We complete the octets. You count, you'll see that we have 4 too many electrons. I can remove a pair here, remove a pair here. What am I going to do? I'm going to take this lone pair, I'm going to move it right into the middle. So I'm just going to move that pair of electrons in. So it's just getting moved over. Now my carbon has his octet. Nitrogen doesn't. How do I make nitrogen happy? I take this pair of electrons and I'm going to move it right there into the middle. Just going to take that pair of electrons and move it into the middle. So when I do that, there's no more lone pair there. And there's my Lewis structure for the cyanide ion. A carbon with a triple bond to nitrogen with a lone pair on each of those elements. One thing I should bring up here, you're looking at this structure for the cyanide ion, and just a minute ago we had the structure for the carbon monoxide ion. You might notice how similar they are. Just blipped out here, just lost the video. Shoot. Oh, there we go. Okay, so you might notice how similar these two are. One reason we care about Lewis structures, the structure of a molecule tells how the molecule is going to behave. These two are amazingly similar. Carbon with a triple bond to a real electronegative element. Nitrogen's one of the 3 most electronegative. Carbon, triple bond to a real electronegative element. Oxygen's the 2nd most electronegative. A lone pair on the real electronegative thing. A lone pair on carbon, which is kind of rare. You don't see too many molecules having that. Hey, these two things have almost identical structures, so you expect them to behave in almost identical ways. Indeed, they do. They're both deadly poisons. They both kill you. They both kill you the same way. It turns out a pair of electrons here on carbon, when the carbon has this triple bond to a real electronegative thing, that pair of electrons is going to grab onto any iron ions in your body, and it's going to prevent the iron ions from functioning properly. Turns out it does this in your cytochrome system so that your cells can no longer make energy, and so that's why these two things kill you. They stop your cells from metabolizing and producing energy. So again, the structure of a molecule determines how it behaves. If you look at the structures of similar drugs, if you were to look at the Lewis structure of morphine, heroin, codeine, they're all very similar. Similar structure, similar behavior. Okay, let's do some more of these. And again, you might want to pause the video, see if you can work through them on your own. If you can't, I'll be showing you how to do them right here. So, ozone, O3 here, very interesting stuff. It's a highly reactive molecule. It's a so-called allotrope of oxygen, so instead of O2, it's O3. So, how many electrons here? We have 3 3 oxygen atoms. Oxygen's in group 6, so 3 times 6 gives us 18. So when we're done with this structure, we have to show 18 electrons. Skeleton structure here, pretty simple. We'll have oxygen connected to oxygen connected to oxygen. And at this point, I'm going to the whiteboard. So for our ozone molecule here, for our ozone molecule, you have your oxygen to oxygen to oxygen. Outer atoms, he's an inner atom. These are my outer atoms. And the next rule says to complete the octets of the outer atoms. So I'll go ahead and do that. There we go. After you complete the outer octets, you take a head count. How many electrons have I used? I've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got 16, but we're supposed to have 18. One of the rules that will really save you, if you have leftover electrons, remember we're supposed to have 18 electrons in this structure, that's what we need, but we only have 16 of them here right now. So we have 2 leftovers. Leftover electrons always go on the central atom. That rule will really save you a lot of grief. So after you complete the outer octets, you count, you see if you've used all your electrons. If you have leftovers, leftovers go on the central atom. So that's where we're starting with the ozone here. Now, how are we doing on the octet rule? Well, this atom has 8. This atom has 8. This atom only has 6. How do you deal with that? Oh, yeah. If the central atom doesn't have enough electrons, you take a lone pair, turn it into a bonding pair. If you look at this oxygen atom now, he has 1, 2, 3, 4, 5, 6, 7, 8. So he now has an octet. This oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. He's got it. This guy clearly has his octet. That's a good structure. That is indeed the Lewis structure of the ozone molecule. This might be a good point to show you that the way you orient it on the page doesn't matter. This would still be a correct structure even if you had drawn it top to bottom. Some people get upset when they're first doing Lewis structures because they might do it this way and in the back of the book they show it this way. It's the same darn thing. It's the exact same structure. Don't get upset about the orientation on the page. For what it's worth, there's another perfectly good way that you could draw ozone if you had ended up drawing a cyclic molecule like this, and you gave each of these oxygens one lone pair. You would have satisfied the octet rule. You would have used the correct number of electrons. If you did that on a test, I'd have to give you credit for it because you're actually satisfying all the rules. We just know that ozone is not a cyclic molecule. Cyclic molecules do exist, but ozone does not exist this way. We know that ozone is not a ring structure. So if you came up with that structure, you're just thinking outside the box. And you're actually exercising good problem-solving skills, I gotta say. So that was our ozone molecule. Next one for us to play with is carbon disulfide, or CS2. Again, you might want to pause the video, see if you can work through this one on your own. I'll show you how to do it here in just a moment. So for CS2, one carbon atom, 1 times 4, that's worth 4 electrons. Oops, 2 sulfur atoms, so that's going to be 2 times 6 is 12 electrons. Add this up, 16. So when we're done with this structure, we have to have 16 electrons. Now, our central atom here, of course, will be the carbon. So we'll start with our carbon atom in the middle, connect it to a sulfur, connect it to another sulfur. There's our skeleton structure. The rules say complete the octets of the outer atoms. Completed the octet on that outer atom. Completed the octet on that one. Next we do a count. How many electrons have we utilized here? Looks like 16 to me. So we're not going to add any electrons. We're not going to take any away. We got to ask, is everybody happy? Does everybody have their 8 electrons, their octet? Carbon's definitely not happy. I can take this pair of electrons and make it into a bond. Now my carbon atom has 6 electrons, but he has to have 8. Oh, I'll take this pair of electrons and turn that pair into a bond. That's my carbon disulfide. That's the Lewis structure for the carbon disulfide. Okay, moving on here. Methanol, this one's a little bit trickier in that the skeleton structure is not obvious. So any of them that are this complicated, I'll give you a hint as to the skeleton structure like I've done here. I've told you that it's a carbon with 3 hydrogens around it. So the skeleton structure on this guy is going to be carbon with 3 hydrogens. Remember, the hydrogens have to be terminal atoms. They kind of end up at the end of a structure. They're on the outer periphery of any structure. So that's our H3C. The carbon is then bonded to an oxygen, which is then bonded to a final hydrogen atom. That's your skeleton structure. Now, how many electrons are we supposed to have here? We got 1 carbon, so that's 1 times 4, that's 4 electrons. We have a total of 4 hydrogens, so that's 4 times 1 gives me 4 more electrons. We have 1 oxygen atom, so 1 times 6 gives me 6 electrons. Add all this up, it's going to be 14 electrons. Now the rules say, hey, complete the octets of the outer. Do I complete octets on hydrogen? No. Hydrogen never gets an octet. My carbon has his octet already. That carbon atom already feels like it's being touched by 8 different electrons. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. The only guy that needs more electrons is the oxygen. So we'll put them there, and that's my 14 electrons, and that's the Lewis structure for methanol or methyl alcohol. That's wood alcohol. That's the type of alcohol you don't want to drink. If you drink that type of alcohol, it will either make you go blind or it will kill you. So a lot of people have been poisoned over the years by drinking wood alcohol or methyl alcohol, also known as methanol. So let's see, do we have any others here? Nope, those are the examples we have. To get good at this, you would probably want to go and try some of the recommended end of chapter problems. We have lots of practice problems for you here. So that's going to conclude this video. And again, you want to try these practice problems. The second half of this packet deals with the shapes of molecules, and we'll go into that in the next video.